Hi, Chem12. So I got a couple of questions I'd like to go over that students raised. One was from page 176, number 128. So here you're doing a titration, and it's a continuation of question 127. So it's basically doing the same exact titration, which is using a weak base called aniline, and then zero point 0.1 molar HCl. So those are the two things that are being titrated against each other. And so what the question is asking is, suppose both the aniline and the HCl, their concentrations increase by a factor of 10, right? So that means like the HCl would be instead 1 molar. So how is that going to change the half point volume pH? And so it's going to have no effect. Okay, so why is that? Okay, so there's going to be no effect. So if you think about that, let's look at the graph. Okay, so here's a graph of we're starting with a weak base, the aniline, and so you see how there's a little bit more of a curve on this part of it, and then we're ending with the strong acid. That's why this one is flatter. Okay, and so here's your half point volume of the titration, which is where your end point is going to be contained. And remember, at the end point, what we have is a neutralization to some effect, right? It could either be a pure neutralization, so this occurs at pH 7, or it can be either acidic or basic. So in this case, your endpoint pH right over here, this would be less than 7, okay, because we're using a strong acid HCl. So at the neutralization point, your moles of acid equal moles of base. So if both of these are going to have a 10 times stronger concentration, that means the moles themselves will be 10 times stronger here, and the moles over here will be 10 times stronger. So remember what this is looking at. This is concentration times volume, right? So and then we're changing this by a factor of 10, right? So this is like one of them, and then here's the other one by a factor of 10, right? So concentration times volume is equal to moles. So basically what's happening is this 10 is just being canceled out. So therefore you're left with the same volume that you had in the first place, right? And so you're left with the same volume, and then the pHs are going to be the same as well. Remember, it's not the pH of the acid that you're looking at, or the pH of the aniline. It's the pH here is the pH of the mixture itself, which now has been neutralized, right? So I think that's where the confusion came from. So the pH then is going to be exactly the same at this point, and the graph will look exactly the same. Okay. Now, if one of them was 10 and the other one was 20, now that's going to have an effect. Okay. All right. Let's look at the next question I got, which was question 181. And that question for 132, question on page 181, question 132D, is basically saying, is this a buffer? Okay. You've got 1.5 molar and 1.2 molar. Here's your weak acid, and this is your conjugate weak base. So that's, remember, your buffer system has to be a combination of the two. So definition of a buffer is a solution containing appreciable amounts of weak acid and its conjugate weak base. So here's the key word. Basically what appreciable means is that you have quite a bit of both. In a regular weak acid ionization, so say we look at something like HA going to H plus and A minus, right? So for a typical weak acid system, what's going to happen here is, because the ionization is poor, you're going to have a little of this, and you're going to have a lot of that. Okay, so there's going to be a big imbalance between the two. A lot of this one, because very little of it ionizes, and that's why you have just a little bit of the ionization products. So appreciable basically means that you have a large quantity of both of these. And so I think the misconception was that they have to be always equal. Okay, so typically when you do set up a buffer system, you do set it up so that they're equal, because then you think of a balance and you've got a counterweight. But here again, because they're large amounts, That's what appreciable means. They will act as a buffering system. So this would be a buffer then. Okay. Again, just contrast that with a weak acid, typical ionization. Okay, so what I want to do now is finish off the unit. Then I'll give you basically a practice quiz to work on for the second half of what we looked at, and then I'll give you the unit test on Friday, and then you'll have till Wednesday to hand that in because Monday is Victoria Day, I think. So we talked about, we just finished talking about what the definition of a buffer is, and so buffers also exist in biological systems. So in a biological system, this term homeostasis, basically what that means is all the different vital signs you want to keep within an acceptable range. So if you think about things like body temperature, right, or you think about heart rate, blood pressure, all these things need to be in a certain range, not too high, not too low, where they can get to dangerous levels and then have an adverse effect on the body. So one of those things that needs to be kept within a normal range is blood pH. So the optimum pH is 7.35, so very slightly basic. And so the blood system itself has a buffering system, which is the CO2 and the HCO3. And so, and the other importance of the system is it also regulates how much oxygen you need. The misconception is that when you are breathing heavily, the oxygen level is determined by how much oxygen you're bringing in. It's not the oxygen that you're bringing in. It's actually more to do with the carbon dioxide you're getting out. So the more carbon dioxide you're getting out, that's a signal to the body that it needs to bring more oxygen in. So what happens is it's a two-step reaction. So here's CO2 gas that's exhaled. Most of it's exhaled, a little bit's left over and transferred to the aqueous form, and then this aqueous form then is sent through the bloodstream. And it's in this reaction, and the H3O plus here, this is going to dictate what the blood pH is. So the buffering system here is basically in place to keep the HCO3 plus at a stable concentration, so it doesn't fluctuate to extremes. Hyperventilating can cause a blackout. So a blackout is basically is due to not getting enough oxygen, getting unconscious, and so this is specifically is caused by the pH getting too high. So what's happening here is when you're hyperventilating, so you're really breathing quite hard, so you can't sort of get your breathing rate back to normal. You're exhaling too much CO2 rapidly, and by doing that, you're not allowing it to convert to the aqueous form. So what happens then is the aqueous form here is going to get reduced. The equilibrium is going to shift left, and it's going to shift left, and then it's going to reduce the concentration of hydronium. And so if you reduce the hydronium concentration, you're going to cause the pH to jump up, and that pH jumping up is what has an adverse effect, and what causes someone to basically faint, okay, as a result. Okay, next let's look at metal and non-metal oxides. So the relation here to acid and bases is that metal oxides and non-metal oxides both react with water, and basically what you should know is that a metal oxide will react with water to form a base, and a non-metal oxide will react with water to form an acid. Okay, and you don't need to be too familiar with the reaction. Just be aware of the general trend. For the metal oxides, where the metals we're talking about are typical of group 1 and group 2, not all metals will do this. And the non-metal oxides, these are going to be covalent, right? Remember, because you've got compounds that are a combination of non-metals, right? So the carbon and the oxygen are both non-metals. So these are going to be covalent compounds. So these are some examples of some of the acids that can be produced. Now, in terms of the relevance especially of the second point, this has to do with acid rain. Okay, so acid rain is basically a result of industrial emission. So emission of things from like car exhaust or from smokestacks. So these are things like nitrogen oxides, carbon oxides, sulfur oxides. So again, these are all non-metal oxides that go up into the atmosphere. And then what happens is they mix with the moisture, and then they come back down, and they have a pH that's less than 5.6. Okay, so there is a slight acidity of rainwater of 6.4, and that's because of the naturally occurring carbon dioxide that's emitted. So if you think about all living things are emitting, mammals are emitting carbon dioxide. Now, one of the good things about Vancouver is because of the rain that we get, we oftentimes don't allow the gas to accumulate in the atmosphere. The rain actually kind of, if it rains often, it doesn't allow those levels to accumulate. You do notice in the summer where there's especially areas that there's a high density of cars and industrial areas, that you do see the sky sort of change colors a bit, get a little bit more brown, and so that's that accumulation. It'll be interesting to see what happens this summer with not as many people driving around because of the coronavirus, if that'll have less of that smog accumulating. But it's definitely like cities like Los Angeles where there isn't as much rain, smog becomes more of an issue, as well as countries that do a lot of burning of coal, right? So that would be an example of a fossil fuel. In parts of India right now, again, because of the reduction of everything, some of the Himalaya mountains now are becoming visible for the first time in a long time, just because of that level of smog decreasing. So basically that's how acid rain is formed. And then there's obviously negative consequences of the acid rain. And so here's some examples. When you see buildings and metal rusting, oftentimes that's due to the acid, the acidity in the rain. So that's an example of chemical weathering. When you talk about three different types of weathering: biological, chemical, and physical. Okay, so I'll stop there. So just be familiar with the behavior of metal oxides and non-metal oxides in terms of what type of relative acidities results when they mix with water, and then just be able to explain how acid rain comes to be and some of the damage it can do. So you can work on these two questions here, page 188, 146, and 147. I've got the acid-base quiz number 2. I just wanted to do this as practice, so you don't need to hand that in. What I'll do is on Friday's class, I'll go over the answers to the quiz, and then I'll give you the unit exam. Okay, so again, the unit exam will be given on Friday, and it'll be due, like I said, on the following Wednesday. So let me know if there's any questions from the unit that you want me to go over. So any of the stuff from the beginning of the unit to where we are now. And so I'll go over the practice quiz, and I can go over any questions that you have before you begin the take-home exam. Okay. So again, stay safe, and I'll talk to you again on Friday. Okay. Bye now.